abbreviated version. Trying not to postpone much on the flow. I'll be discussing a flow, channel flow, that is subjected to a span-wide shear during one of the moving walls in the lateral motion. I was introduced to this flow quite a while ago when I went to UCLA to work with John Kim and Benjamin Lee. But I thought it would be worth looking again at it because of what it may be able to tell us about flow control issues and the fundamental dynamics of near-wall turbulence, especially in light of some of the recent studies of streaks and hairpins and so on. So I'll let you be able to judge that. It's a diagram of what the simulation involves. It's just, as I said, a standard plane pressure turbulent flow, and at time t equals 0, we suddenly jerk one of the walls in motion and hold it to constant velocity. And this diffuses a Stokes layer into the turbulence, and this creates this curious behavior. This is a time-developing parallel flow analogy to the experiments that are found, for example, on a transverse flow along a pipe with a circulating section, or on a sort of treadmill thing in a sideways direction. And the same kind of qualitative things you see here. This is one of a number of studies that were started back in the 1990s. The first was done by Wayne's group, where they suddenly applied a span-wise pressure gradient, but because of the parallel flow nature of the channel flow, that amounts to accelerating the walls in the opposite direction. So we're doing qualitatively the same thing. Actually, Niels has looked at this flow as well, and then there's been some increasingly complicated variations of it. If you oscillate the wall laterally in time, you get a certain kind of carries on. And then nowadays, people are also looking at streamwise variations in the span-wise velocity. But we'll be focusing just on this. And I'll be showing you some of the results that Antoine did for his thesis, all did at Reynolds, Cal 180. And some new results, which are roughly twice the numbers with about the same magnitude. And I'll have two perspectives here. One is just looking at the statistics.
Excuse me, the ratio is to the average velocity or to the peak center line velocity?
That's
the
initial
U-top. Okay.
Yeah. WS plus.
Okay.
And all plus units, I should say, are with respect to the initial value of the function. All right, starting out looking at the statistics. First, what things change. This is moving downstream, if you will, and we set the wall in motion, and then you can't really tell it, but there's a blow up of the wall. You get the Stokes layer that comes in over time. And the rather curious thing, and why we're interested in it, is because at the same time you get this increased span-wise shear, you get a decrease in the streamwise shear component. And that's a bit bizarre when you think about it, because usually if you have a turbulent flow and you apply shear to it, you're straining it, so you're doing work over a distance and you're putting energy into the flow. So you think that turbulence would respond by becoming more energetic. But both the turbulence, the kinetic energy, and the shear stress and the drag go down. And you don't have to think too long to realize that that might have some profound flow control implications. You'd like to understand the fundamental issues associated with that. And this is just to remind you that all the plus gains here are with respect to the initial values. Okay. So the basic question is, what's up with this? What's going on? This is a history of the streamwise drag, as you see it. Why does applying a shear in an opposite direction cause the streamwise drag to go down? In an attempt to get at that, I'll show you some profiles of these different First, a quick look at how dependent this phenomenon is on Reynolds number. This is a history of Antoine's study at Cal 180, and this is a new one. And you can see we get at least this deep a drop in the drag. There's some ambiguity that I've accidentally introduced here because when you first set the wall in motion, you can't just, you've got to have a bit of a variation in the span-wise wall component. So you put an analytic Stokes solution in there. You need to choose your length scale of what distance it varies. So I try to keep it quite small. But I set it, I had the code set up so that that was a fraction of the half width. And I use the same 1% half width here, so it amounts to jumping forward a bit in time. But the main point is just that, at least over this Reynolds number range, you get the same drop in the Now, looking at the real stress budgets and trying to answer this question, why is the drag drop? If we consider the so-called FIK relationship now of Gupta in Kasabi's group, and they showed that the skin friction or pipe flow is directly related to the profile of the renal shear stress, weighted by the distance from the wall. So if you put that weighting in here, you focus in on the profile, the shear stress profile, amplified the urology studies and logarithmic scale. This drop in the shear stress can be thought of as being primarily responsible for the drop in drag. So what causes that? We've got the statistics. We're going to look at the budget now of this quantity, the shear stress at that time, and see which term is most responsible. And it's a bit of a messy plot. I'll get to the main result in a minute. This just shows the changes in each of the terms in the shear stress budget as a function of time. So if you look at one of these shaded regions, the one that's the biggest is the one that's doing the biggest change. So you can see that that's the one that's
Dash is light on.
well, the different symbols are different. The different line types correspond to different terms in the budget. The black line is the initial condition of that quantity, and the shaded regions tell you how much change has been induced by the span-line shear motion. And what we find is the two big players are the production term and the velocity pressure gradient term. And you can also, if you want to zoom in a bit more, if in the interest of time, we'll just skip over this to the main result. If you look a little bit, you can see that with regard to this change, it's caused, so this is defined as the wall normal variance times the shear stress. You can see which one of these changes the most. What we find out is this is the one that's changing. And so if we look at the budget for that particular term, we see also again that the main change there is also due to this velocity pressure gradient correlation. Why do I trouble you all with that? It's just to get to this main result. That from a statistical point of view, all the changes are due to this nasty pressure gradient velocity correlation, which means this isn't going to be very easy to model at all. It's a bit disappointing because if you're interested in examining different flow configurations, maybe say design studies maybe for flow control, you're not going to be able to tell very much certain things in a Rand's approximation of this very simple flow. Okay. Quickly, I'll go on to say one thing I think again from the statistical perspective. The difficulty with this kind of, one of the difficulties with this kind of flow is that this span-wise shear profile that walks or diffuses into the flow varies as a function of time. It gets diffused over a deeper layer as you goes on, but also it weakens. So we got very cheeky and decided to do something only a computationalist would dare. And jump in and do a very artificial synthetic numerical study. So we just, for the initial time of this turbulent channel flow, we went in and we just imposed, pasted on, if you will, a span-wise velocity profile and held it constant in time. And we did this for different depths of the layer. We just went in at different places, keeping the shear the same, and therefore increasing the velocity. For different magnitudes of the shear, here is a function of the initial wall value shear or amounts to dw constant y+, and increasing the region over which the span-wise shear was applied, and just sort of.
It doesn't enforce. I mean, we have to do something to keep that.
Effectively, it amounts to a force. We've fiddled with the equation so that it implicitly defines a force. And this is a pretty tedious easy plot too. So I'll just jump to the conclusion. These are the three different histories of the streamlines drag and how they all decrease for the different magnitudes of the shearing and for the different regions over which the shear is applied. And if you look at these, it takes a while to sort it all out, but the main conclusion is here. You get the biggest change when you apply the shear between this region of 5 and 15. With the downward shift increasing magnitude. That's consistent with the oscillating Stokes layer behavior for reasons I don't have time to go into now, but I'll talk to you about that later. But the main result is that fiddling with things between y plus of 5 and 15 has the deepest, most profound effect on the drag reduction. And we'd like to understand what that means from a structural point of view. Given all that statistical information about the manifest budget and this idea of optimal shearing, we went on to think about the structural perspective, and Antoine did lots of staring at the flow visualizations, trying to understand what's happening. Maybe this is a good way to summarize the issue. Again, there's a history of the drag reduction. This is from the lower 180 case, but the training result is the same. And these are streaks at different times. This is a 2D state, and what you can see, I hope, is as the flow is turned, what we're doing is we're moving the wall in this direction, which amounts to applying an effective favorable pressure gradient in the opposite direction. So we're turning the flow in time to the right. But what you can see at these different times is that the streak patterns very near the wall start to have changed direction. They're sort of shredded, broken up into little bits as it moves this way. Eventually you get at later times. But even before it recovers to an effective 2D state, you see this sort of realignment of the streaks. Why is that? Well, there's been a number of proposals that have been put forward to try and explain this kind of behavior. Here's a summary of them. They all tend to involve the quasi-streamlined vortices, or PSV for short, modifying the vorticity, their string, modifying the trajectories around them, shifting the streaks beneath these vortices, or somehow breaking communication between the vortices and the streaks. So, different references. Now, these are going to overlap to some extent, and also it may be in the real flow where the shear layer diffuses in time. It might be that one mechanism is more important than the other, so it's a bit of a mess. But one thing we can say is that all these theories, at this point, tend to have these common characteristics. They tend to view things in terms of just looking at a plane, a span-line vertical plane, and the vortices around them, and think about the induced velocities as if the vortex were the 2D version. And also there's a tendency to view the vortices and the streaks as separate entities. So that sort of makes sense within the context of the usual model about where streaks come from, I guess. But I think there's a bit of a danger here. Antoine used the latitude criterion, again, to look down on the walls, and these are the streaks that are induced at y plus 5, and this is a cartoon which was put forward to explain what's going on. And I was talking about a danger. I think within the conventional thinking, you can see this, but it's sort of like a hot dog in a bun. The hot dog is the quasi-streamlined vortex, and the bun is the flow that's induced around it. And I think it's fair to say that at least in the well, it's as if these things are being drugged through the flow, the standard model, and these induced velocities are the cloud that induces the streak. And so there's going to be a region in which the thing's swirling around and marking the flow, and then the long streaky bits are just sort of where the downwash used to be. I think that's one fair way to describe the mechanism by which streaks are induced. But at least in the upstream end, or the regions of the streaks near the quasi-streamlined vortex, there has to be a dependence between the interdependence between the vortex and the streaks. Because after all, if the velocity is induced by a vortex, the vorticity and the velocity are just two sides of the same coin, just 3 units apart. And I think some people maybe have been played a bit loose, myself included, and had one of those theories there, in breaking the communication, tending to think about the velocity as a separate entity from the vorticity. Now, you can do that if you go far enough downstream, I think, but there is a danger there. So with those kind of warnings in mind, Antoine looked at all this and tried to take into account the shapes of the quasi-streamlined vortices. They tend to be lifted a bit and hooked, at least in this model. I think that's a fair summary of what happened before. And what you can see if you zoom in on the flow after the span-line shear is applied, you see that things that look like, used to be, say, a left-hand parentheses, get a kink in the bottom. So a left-hand parenthesis becomes an S shape, whereas a right hand closing parentheses becomes more J-shaped, and things get twisted that way. And if you adopt that kinematic model, you can explain what happens both in terms of the drag reduction and the asymmetries in the statistics. What happens is it's sort of like the difference in the strength of a downwash of a line vortex and a vortex ring. Because you've got a curved bit of vorticity, its effect is going to be stronger than a straight bit. And that's the way Antoine justified it. And it does have the advantage of treating the quasi-streamlined vortices and streaks as unified structures. But on the other hand, this is the reason I thought it'd be worth looking at all this again. To be provocative just before lunch, I think that there's a question, mostly based in the fairly recent work of Turner, Schenkel, and Begg about the dynamics of what's really going on in the relationship between quasi-streamlined vortices and streaks. Are they really necessary? I think we need to answer this question because it poses a challenge to the field. What Sergey and Mirza found through these numerical experiments was that there's an alternative way to describe where streaks come from. If you just put random vertical wall fluctuations in the flow and think about the shearing that happens and then the diffusion across that shear layer, you can also get streaks. And here's the main, this one and the next one are my sort of summarizing bottom lines. This is the numerical experiments they did. These are just scans from their paper. These are the streaks involving contours of streamlined velocity fluctuations. And has been pointed out a few times over the last few days, the streamlined velocity component can be thought of as behaving essentially as a passive scalar. This is the contours of a passive scalar equation that was solved at the same time, embedded in that velocity flow. And the way they did that was they just, for the convective term on the scalar transport, again being very cheeky with the physics, only numerical DNS books can be, they put a mean one component of velocity with a normal variation, and superimpose on top of that random gravitational velocity fluctuation. And they put a body force in there so that the shear variation of the flow matched the wall normal variation of the mean scalar. And the conclusion is you can also make streaks by other ways. I guess that's been found before, but I think it's worth thinking about. The final thing I'll show you from their experiment is that also in the same flow, the same velocity field, they put different mean scalar profiles in it, and they get different streaky patterns in the scalars. So that would imply perhaps that quasi-streamlined structures aren't essential. Certainly, I think it's fair to say that they're not essential to form streaks. Are they the dominant mechanisms for creating the wall shear stress? I think it's probably the best we've got at this point. But I do think it's worth taking this on board and understanding the challenge that this numerical experiment represents to the conventional thinking on this. So I'll just say it. I'm not making you read that if you like. You can get good readings in statistics despite the fact with different DNS, despite the fact that some of the DNS have lots of structures in them and other ones don't. So here's my summary. If you're going to model this flow successfully, you're going to have a pretty smart triple model. One that doesn't exist yet. You have to use velocity and pressure gradient correlations, right? The Reynolds number dependence wasn't a problem for these numbers considered here. We found that the greatest drag reduction when we applied spandrel shear with that region. And finally, the main reason I'm thought it would be appropriate to talk about this flow here is this open question that remains regarding the dynamic significance of quasi-streamlined vortices and the relationship with the wall surface. And that I'll stop.
I mean, you have also, now you get also some water stress in some of the spandrel effects.
That's right.
If you take the absolute value of that, is that still a reduction compared to the smaller than the
It is initially, but eventually you get a new effective 2D flow in opposite direction. That's why they tended to oscillate the flow. because you can just sort of keep the turbulence off balance, and it generates a lower drag state. Whether or not from a practical point of view you get more than you pay for is a bit tricky. I think you can in principle, but you can't just, the things you can do numerically wouldn't necessarily be practical practice. But you have to oscillate.
But still, the absolute value of the shear stress is less than the value of
Yes.
But are the streaks aligned with the friction line or the friction vector?
Not instantly.
No.
That was what this that one plot showed. Is that it takes a while for the new state to it takes a while for the new stress is pointing in a new direction here, but still the streets keep a streamwise orientation for quite a while. It gets shredded in a sense. But the question is, does that matter dynamically? Is this a passive signal of what's going on?
Yeah, I mean, I can see the big difference between putting a random V and random vortices, because if you have a random V, you have a degree set in this omega.
Yeah, it might amount to the same thing, but I think sometimes maybe it's just the model that we have in our head.
I think it's just a question of whether you put the vortices or put it there or something like that.
Yeah, maybe, but people like to think about regeneration cycles and having a simplified model of the dynamics of what's going on in terms of coherent structures. And I think people have latched on this idea as the quasi-streamless vortex as an essential link in the cycle. Yeah, okay. Yeah, okay. Yeah, it might be that. Yeah, it might be we're trying to read too much structure into what's happening, and that might be the answer at all. But so what's what?
I actually wanted to go into this question that Jimenez was raising. Actually, here in the place where the concept of transient law was born, it is not difficult to understand that if you perturb somehow the flow, then you get streaks. But the point is how they are related to such a sine cycle. So I would like to have the comments also from other people in the audience about this concept, because are these streaks, so to speak, scientific streaks that you could able to survive? I mean, if you trigger by a random velocity, then they go on, keep on living, or they die out eventually. I mean, because this should be related to the.
Well, I think they live on. Yeah.
So they create vortices in a sense. Or
Well, but how do you explain the streaks in the scalar field embedded in the same velocity
Well,
field?
aren't you violating Hunter's Stokes by doing that? It's sort of a contrived, you're playing around with this scalar equation here, but you can't superimpose a velocity field, assuming it's linear and stuff.
That's true. Yeah, this is a passive scalar. It's not, and it's forced. Yeah, okay. But it tells us something, that you don't have to have the real vortex-containing velocity field convecting the scalar around to make streaks. I think that's the main message that comes from this. These are irritational. These are just solutions to the velocity equation.
That's basically what's known. That's RBT. You put any V, you create a streak.
Well, I didn't hear the last bit.
Yeah.
Yeah. But it all, okay, fair enough. But I don't see how that connects with the regeneration cycle and our ideas about the coherent structures near the wall associated with it. There seems to be a link missing.
Yeah, I mean, you still have to create vortices. Or something that creates V. I mean, you have to create something that creates V.
You need to create V.
Right.
We did this oblique transition experiment, trying to measure streamline vorticity. It's unmeasurable. It's less than 1%. I mean, it's so small, but the streaks are extremely strong. You get 20–30%, in the euros. So the streamline vorticity would actually be extremely low. Also the V is
The question I have is, in this context, what does that mean for an experiment like this, where you fly a span on shear in a certain region and the drag goes down? What is that? What's happening?
Look, just in a rising of this situation, and you put a stochastic forcing curve like that. It is known that what is most simplified are the streaks. Whatever you put. Now the question is that the minimum energy course, the same field of streets are streamless vortices. So this is the idea. Compared to what you put here, streamless vortices require less energy. So this is probably why they are important, because with the same amount of energy, they can give larger active streets. This is probably how they can be refitted. This is Farrell and Johanno, they found it like 93.
But then on top of this, the problem that in turbulence then you are not able to, I mean, this is for the stability.
No, it's not the stability, it's just the linear operators, you're not looking at
Yes,
anybody.
but when you have turbulence, then everything gets non-linear, so you should have the destabilization streaks and regeneration. I mean, it's...
Yeah, but from the streets, the most efficient one is streamless vortices. Even if you have a very low amplitude of streamless vortices, they will have the most amplified streets. In stochastic, for example.
Well, thank you. I've got to take off after lunch, so if anybody wants to soak me up, drop me an email, please. Talk about this further, and please hear your thoughts.
Okay, thank you.